Perfect. Thank you for the introduction. Lots
Yeah.
of details. So I'm actually running this startup called Cleanlab nowadays primarily. And what we do is we focus on building software tools for data-centric AI. And so that's what I'm here to tell you about. And that's sort of this really new area that's emerging, and there's a lot of hype around it. But, not a lot of clear scientific and engineering principles have emerged. And so that's what we are trying to establish at Cleanlab. And so obviously everybody who's worked with real world data knows that your model can only be as good as the data it's trained on. And, the data itself is always the most foundational step in any sort of machine learning analytics project. You need to make sure that you're not doing getting garbage in, because you will get garbage out. And these models tend to be really brittle when you're fitting them to, say, noisy labels or data that's corrupted or has other kinds of issues like bias in it. This is sort of very common sense. And so basically in real world machine learning applications, unlike how most of you probably learned machine learning in a classroom, the company that you work at or your users, they don't really care at all, what kind of clever machine learning algorithms you use or what tricks you use to give them accurate predictions on some nice data set. The real world data will be very messy, and so you can spend a bunch of times fixing the data itself. And in fact, we found that 10 of the most widely used machine learning benchmark datasets are full of labeling errors. These are data sets used for evaluating, the progress in machine learning and studied by thousands and thousands of researchers. But actually the labels that are being evaluated with are just wrong. And we collected, all the incorrect labels on this website, labelerrors.com, that I encourage you to go check out. And we published a paper that you can see below. And so everybody who's been working in the data space, after a few years, you get some experience and you quickly realize it's like a lot more worthwhile to invest your time in exploring the data, fixing it up, than it is to spend your time, tinkering with models, like hyperparameter tuning them, trying different training recipes. You often realize you get all the big gains by finding some big problem in the data set and fixing it. The problem is this is really manual labor and very ad hoc and guided by intuition, and is really hard to do for big data sets. And so we at Cleanlab and in this broader data-centric AI movement think about how can we use software to help automate this process of finding and fixing problems in the data. So how you might think of the standard pipeline to produce good machine learning models in real world applications is typically you have some data set, you explore it, you find some very fundamental issues in the data, like, oh, I need to delete this whole column because it's totally messed up, or things like that. You transform your data to be appropriate for machine learning, maybe pulling out of multiple databases and merging those features together. And once your data is in the right format for machine learning, then you'll typically train a baseline model, something just using some package that you're familiar with and gives you pretty good results on most data sets. You'll train that on your data and you'll see how it does. And then typically people are tempted right after that to start jumping into all the modeling techniques you learned in class and in your education on how you might improve this model through, regularization, different objective functions, different training procedures, model ensembling, all that stuff to try and get the best possible model you can get. But actually, what we propose is really you should do a second step. After you have your baseline model, you should actually use that model to check your data one more time, because a trained machine learning model knows a lot about data and can help you understand your data set much better. And essentially, that's a big focus for us in this space of data-centric AI, is using AI itself to understand your data better, such that you can then improve the data and get even better AI. And the idea here is that all of this will be much more automated and systematic than the initial data exploration you're doing. You're going to use your model's representations and predictions of the data and feed those into algorithms that then help you understand different kinds of issues you have in your data. And that systematic process will be much more reproducible, and it will give you much broader coverage on finding different kinds of issues in data. It's not just, searching for problems that you happen to think of in the moment. And then once you've done that and improved the data set, then of course you can go back to now trying to tinker with different modeling techniques to try and get the best possible machine learning model you can. And because your data has now improved, you'll often notice that you need to do much less tinkering on the model side, and maybe even just retraining your original ML model. The baseline works great on this improved data set. We often find that. And so, yeah, the real principle here is not just, improving data, because that's what most data scientists spend most of their time doing. It's all about using automation and machine learning and AI to improve your data so that you can get better machine learning. And really the goal there is to make this a science, as I mentioned, and an engineering field of improving data itself. And I think, as was mentioned in the introduction, I recently taught a course at MIT on this topic. I think it's one of the first courses ever on this topic, so you can go check it out at that link if you want to learn, a lot more details than I can cover in this talk. And so what are some of the hype around data-centric AI? So of course, OpenAI is the most hyped up organization of all time right now these days. And they train these very, very famous machine learning models that are arguably some of the best machine learning models in the world, right? And so people might think, oh, they are experts at these modeling tricks. They came up with these really innovative ideas on the machine learning side. But actually, most of the models they train are just really scaled up versions of models that have been known for a while. And what they spend most of their time doing in training these models is actually curating the data itself to ensure that when they're training this huge, super high capacity model on this huge data set, that they're training it on the best possible version of that data set that they can. And so one of their famous models is this image generator called DALL-E. And we can look at one of their demo videos from DALL-E and look at some of the explanations they have behind how they created this model. And so one of the things that they point out was a major limitation as they're creating this model is, if this model takes in text and generates images. And so if it was trained, with text that was incorrect labels for images, like an image of a plane being labeled as a car, then when a user tries to enter car and generate an image of a car, it might actually accidentally generate an image of a plane. And this is sort of very obvious, but the fact is that they had all these errors in their data and they had to spend a lot of time fixing them. And so, yeah, really, the key here is that they needed images and accurate labels, a good collection of images that were big and accurate labels in order to train such a high quality model that has, really impressed the general public with machine learning. Arguably one of the first demonstrations that has, really impressed your ordinary person as to the power of machine learning today. And obviously the key takeaway here is that when you are training these models that will be deployed in the real world, the quality of data that you are feeding them with really, really matters. Another famous blog post they had on the second version of DALL-E talks about pre-training mitigations that were involved in the image generation side of the model. And again, a powerful tool they used here is this idea of data filtering and filtering out the bad data from their data set. And they argue it's much better to filter out the bad data over leaving in all the good data. It's better to, be more aggressive and remove bad data, because once you've trained your model with the bad data, it's really hard to get rid of that. That's deeply embedded in the model. Whereas you can always add extra data during fine tuning to continue improving the capabilities of your model. So if you accidentally threw out some good data in the initial pre-training phase, it's okay. And it's much more preferable than, pre-training these models with a bunch of low quality examples, because that cannot be gotten rid of. And some of the problems they found in their data set beyond the bad labels included a lot of duplicate images and nearly duplicated images. These are just prevalent across a lot of computer vision data sets, and low information images that led to the generative model tending to produce, very plain memorized outputs for certain kinds of prompts. Another really famous example of a very data-centric company is Tesla, who's trying to train a autonomous vehicles driving system just using cameras alone. So very, very ambitious task that nobody really thought, you could just use computer vision only without any other types of modalities to drive a car. And so the way they have focused on doing this is they have a huge division in the machine learning side of the company that is what they call the data engine. And actually most of the people working on the algorithms behind the autonomous vehicle are focused on this data engine, which is all about quickly noticing what are the problems in the data, amplifying those problems in the data, and fixing them up so that they can train a new version of the model and then use that new version of the model to discover new kinds of issues in the data. And so that's all about what I'm going to teach you today is how do you use an already trained machine learning model to find problems in your data such that you can improve your data and train a better version of the model. And this is a very virtuous cycle, that leads to Tesla having a very advanced self-driving system despite only using cameras. And just to, again, highly give an example of this big difference between the model-centric world and the data-centric world. This is a slide from Andrej Karpathy about how much sleep he lost. So he was the VP of the Tesla AI, and how much sleep he lost during his PhD, focused on models and algorithms versus data sets, and in the real world, working at Tesla, how much sleep he loses over working on data sets versus models and algorithms. And you can see, the focus on data really matters when you're trying to solve real problems with real data. And so the first kind of problem I'm going to talk about, so this talk will be focused on, what are some general types of issues and data curation strategies that we can do that will work for all kinds of data sets. We're not really interested in one particular domain, using your domain knowledge to figure out what's wrong with the data. That is extremely valuable. That is always something you should be doing, but that's hard to automate. That's hard to bring, general engineering and scientific principles for. So we are focused mostly on common problems that just plague data from all kinds of domains. And so if we're doing supervised learning, which, most companies today doing machine learning are doing supervised learning, one of the most common types of problems that appears in such data sets are label errors. And so these are examples taken from the famous MNIST digit classification data set on the left, and on the famous ImageNet dataset on the right, where you have a picture of a 3, and actually the real label of that example in MNIST is 5, and that picture of a 7, the real label in MNIST is a 4. Likewise, you have this picture of a lion in ImageNet, and its true label, given label in ImageNet, is actually a monkey. So you might be wondering, how could this be, right? Like these are the most famous machine learning data sets of all time. They've been studied by thousands and thousands of grad students who have been, trying to boost the accuracy of their model. And, how is it that there's just these not great labels in them? And how did nobody really know about that? And the reason that it's not well known is because it's not easy to find these. And so we have invented some algorithms that can help you find mislabeled data in a data set. And we just ran those algorithms, on all these famous machine learning data sets and found a bunch of errors in them. And you can, again, browse these errors yourself at this website we created called labelerrors.com. And so we ran this on a bunch of the test sets in particular of some of the most famous machine learning benchmarking data sets like MNIST, CFAR, Caltech 256, ImageNet, a bunch of text data sets that are really famous like IMDb and 20 News and Amazon Reviews data set, as well as audio data sets. And across the board, doesn't really matter what the domain is, we found a bunch of label errors. And then we ran our algorithms that I'm going to tell you about in a bit on these data sets. And then we checked some of the outputs from the algorithms using mechanical Turk workers to, ask them, is this really mislabeled or not? And yeah, we found basically a pretty large error rate in almost all these data sets, 3.4% on average. And this was actually work we just did in 2021. So the fact that, this is being discovered only now is kind of surprising, but it was a big deal. And actually, we were featured in like a lot of news articles about this. And, it was very surprising to a lot of people in the machine learning community because they never just spent the time to study the data itself in a great depth. They were just focused all on evaluating models and trying to get better model performance. And so at that time, we essentially had an open source library that implemented the algorithm that we used on all these data sets to find the errors. And then with all this media attention, a bunch of companies started reaching out to us saying that they were using this library. And so that's when we decided to create this startup Cleanlab and focus on this broader idea of data-centric AI to build software that can find other kinds of problems in addition to label errors that just tend to happen in all kinds of real world data. So going back to the label errors, the kinds of label errors you have in such real world data sets, again, these are all real examples, and I'm showing at the top their given label, and then, what our algorithm would correct the label to, or thinks is a better label for this example. And you see that there's different kinds of examples, like we can really categorize them in different ways. At the bottom are examples where they're fundamentally kind of hard, like, even humans don't agree on what is the true label for such examples. This is probably something, worth knowing about is in your data set. Maybe you could give clearer instructions. Maybe you could define your classes a little differently if you're doing classification. But yeah, these are fundamentally hard. Then we have out of distribution examples, which are, super common in all real world data that are just not really from any of the classes in your machine learning problem, in your classification task. They're not even, relevant. They just are data that happen to find its way into your data set. Your annotation team gave them some labels, but it may not have to do with anything at all. For example, in Caltech 256, there's this image of a graph, like a sigmoid type graph here. And it's given a label housefly, which just seems totally nonsensical data. Then you also have data where multiple labels should actually be applying to each data point, but these are all multi-class classification data sets. And that's just the limit of the multi-class classification framework, that it's always saying there's only one class that applies to the example, but it's important to know maybe multi-class classification is not an appropriate formulation for your problem if you're going to include data like this in your data set. And then there's just straight up incorrect labels that we don't know why they were done this way, but they're just a pure annotator mistake where it's very obvious what the true label should be for a lot of these, and it's just not the label that was given in the data set. And again, those are all real examples, and there's thousands of them that you can browse in all these famous machine learning data sets. And so the algorithms we use to find these label errors is based on a framework called confident learning that we published in 2021. And essentially, it's a theoretical algorithm that can efficiently find label errors in classification data sets and rank the data by their likelihood of having an incorrect label. It's also useful for machine learning with noisy labels, where the idea is once you've run the basic algorithm to identify which labels are incorrect, you can just choose to delete them all and retrain your model to get a much more robust model, because obviously training a model with bad labels is not a good idea. Or you can actually try and fix the labels that you can and then retrain the model on the fixed data set, and you get big gains. And you can also understand the label noise in a data set, because sometimes it's all, one class is the one that you're seeing all the label errors in, and it's actually the fact that your annotators do not really understand that class very well. Maybe the instructions on how that class is defined are not clearly articulated. And so the key idea of confident learning is all it takes in is a model's predicted class probabilities. So this is, again, focused on classification data sets, and you train any machine learning model you want on your classification data set for classification. And then you give us the predictions, the probabilistic predictions from the model. And that's the only input required to find label errors with confident learning. So this allows it to just work out of the box with all kinds of data types like image, text, tabular, audio, other modalities. Basically any modality where you can train a classifier model, you can then get the predictions from it and give them to Cleanlab, and it runs to or you can give them to confident learning, and confident learning will run to identify which are the high confidence predictions that we should actually trust essentially the model over the data itself, because these predictions are so reliable that we think the model itself is the correct one and not the data. The data is actually the wrong one. And you can think of it almost as a form of calibration, really understanding where your predictions are reliable versus not reliable is essentially the key ingredient that our algorithm imposes. And so we have an open source library called Cleanlab. And as I mentioned, this has become quite popular based on all the media coverage we got when we ran all the famous machine learning benchmarks through this data set. And it's now used by thousands of data scientists at companies all over the world. And the idea of this library is you can run this confident learning algorithm on any data set with just one line of code, and it will tell you all the labels in your data set that it thinks are incorrect and sorted in the order that it thinks are most likely incorrect to least likely incorrect. Okay, so that covers the label errors section of the talk. And a natural thing to do in real world applications, if you know your annotators are noisy who are labeling your data, is to use multiple annotators to label the data. And so what you might do is you might have 3 annotators label each image and then try and develop a consensus label out of those 3. You might try and ask, how confident are we that the consensus label is actually correct for this image? And we might ask overall, which of our annotators are not doing such a good job and whose labels should we trust less? And again, this is just summarizing those 3 quantities that I just mentioned we might be interested in when analyzing such data. A consensus label, that is our best guess at the true label for this example. Quality score for how confident are we that the consensus label really is correct. And that influences, maybe we want more annotators to go annotate the examples with low quality scores where we're not really sure in their current consensus label. And then a quality score for each annotator, which basically summarizes how correct their overall labels are. Forgive me for jumping into just a tiny bit of math here, but basically the idea is we have a classification data set again with a bunch of examples labeled by annotators, and we don't assume every annotator is labeling every example. Some examples probably are just labeled by one annotator only, right? That's very common in these data sets. And then you have some examples that were labeled by 5 annotators and some that were labeled by 3. And so the most basic strategy, most people use to analyze such data is they define the consensus label via majority vote, where, they measure the agreement amongst all the given annotations for an example and just measure how many annotators agree with the majority vote label. And that is what would be the confidence score and how confident are we that this consensus label is correct or not. And you can also measure the quality of an annotator just by how often did their annotations agree with the consensus label. These are very obvious basic ideas that probably most people jump into when analyzing such data. The problem with these basic ideas is they don't work well when you have few annotators labeling some examples. And that's really the case that most real world data is generated under, because nobody wants to spend a bunch of money having 50 annotators annotate every single example in a data set. And so especially in the extreme, you have some examples with just one annotator annotating them, and the agreement is kind of meaningless at that point. And you're not really getting reliable consensus labels for those examples. You don't really know how good those annotators are if some of them only labeled a few examples that few other annotators labeled. And so we have developed a method called Crowdlab, and just like confident learning, it takes in the predictions from any classifier model you've trained on your data. So again, this works for any kind of data that you can train a classifier on. You give us the predictions from your classifier. Again, they should be probabilistic predictions so that we can assess the confidence of this model in the different classes for each example. And essentially the key idea of Crowdlab is we treat each annotator as another kind of model, right? Each annotator is essentially just making a prediction of what they think the label should be for an example. And then we say, okay, we also have this classifier, it's another model. So we have all these models making predictions of what they think the true label should be, and what's the best way to combine a bunch of models. Everybody knows, who's done Kaggle, the best way is to create a weighted ensemble, and that always gives you the most accurate predictions when you do the ensembling properly. And so we have, some fancy math to figure out how to do the ensembling property based on weights, which we assign to the model and the annotators that trade off between how accurate is each annotator relative to the model. And the result is that even if we have a good model, but bad annotators, we can still get good consensus. If we have a bad model, but good annotators, we weight the annotators more and we can still get good consensus. And so we really get the best of both worlds in trying to figure out, how do we want to establish what the consensus label should be, as well as the probability distribution of how confident we are that this consensus label is correct. And so just showing some really simple results. So here we have a data set called CFAR10, and somebody went through and actually had a bunch of human annotators annotate each image in the famous CFAR10 data set, and they called their variant CFAR10H. And you can see here that we're measuring the accuracy of different ways of analyzing such data to determine the consensus label for each image, given each image being annotated by 1 to 10 annotators. And we actually know the ground truth label for each image in CFAR10. And so we can assess, the accuracy of different algorithms' consensus labels against this ground truth. And we see that the Crowdlab method on the bottom is much more accurate regardless what kind of classifier we use. Here we use both a residual network and a Swin transformer model. And in both cases, it doesn't really matter. Crowdlab gives you much more accurate consensus labels than a variety of other crowdsourcing algorithms, including, this basic majority vote strategy. Similarly, the confidence scores given by Crowdlab tend to align much better when the consensus label is correct versus not correct. So Crowdlab is much better at ranking your data, such that if you were to rank the data based on which examples should I go collect more labels for, you would properly have ranked the examples whose current consensus label is least trustworthy the highest. And it's also very good at the annotator quality estimates it produces are very well aligned with how good the annotators actually are. So we actually measured each annotator's alignment with the true ground truth labels in the data set. And we see that Crowdlab's scores have much higher Spearman correlation with these ground truth annotator qualities. Another related method that we developed for active learning is called ActiveLab, which is just a very simple extension of Crowdlab. If you recall, in Crowdlab, I mentioned we have a way to score how confident are we in the current consensus label. With ActiveLab, you essentially can then go ask for more annotators to review those examples that you're least confident about. And we generalized this to also account for unlabeled data. And so the idea of active learning and ActiveLab is to, given a total set of annotations you are going to collect, choose the examples that should be annotated by one more annotator, such that you will be able to train the best machine learning model under that budget. And I'm going to skip this, but this is just a standard active learning pipeline. The only difference here is that we are allowing ourselves to relabel previously labeled example. So in going back here, when we're trying to decide which data to label next, we could either choose a currently unlabeled example, or we could actually ask an annotator to review the current label that a already labeled example in our data set exists, but we actually are pretty suspicious about its true label because it has low Crowdlab score. Maybe it was annotated by an annotator we later found to be very unreliable. And so the key idea that I want to get across is doing this again with different kinds of machine learning models on real data. You end up, so here on the x-axis, we're showing iterations of labeling rounds. So each round we go collect more labels, we retrain the model. We either choose which examples to label randomly, or we use standard active learning methods like the predictive entropy of our classifier and other uncertainty measures from the classifier, as well as this method I mentioned called ActiveLab. And you can just see the models you train with ActiveLab, given the same amount of total collected annotations, just tend to be much more accurate across different types of models. And we found this holds for different data sets as well. And so all this stuff is available for free and open source in our library Cleanlab. This is what we're trying to build into the standard open source library for data-centric AI, for checking data sets to find issues in them and helping you improve your data so that you can do better machine learning. And yeah, all this stuff that I've been talking about, finding the label errors can be done in one line of code. It can be done for multi-label data sets like image tagging data sets. You can also detect outliers just using the predictions from a machine learning model. You can also detect outliers using embeddings from a machine learning model. That's very popular nowadays, to embed your image or text data, and then you can find the outliers in your data set that way. We have another package called CleanVision that you can run. Again, it has other algorithms I didn't have a chance to talk about that can find different kinds of low quality images in an image data set. It's very important for training generative models that you don't have such data in your data set, but also for supervised learning applications, it can be pretty bad to have these kind of images in a data set. You can do this Crowd thing I talked about for analyzing data from multiple annotators. And again, just one line of code to get all three estimates of the consensus labels, how good those consensus labels are, as well as which annotators are doing poorly. And then you can label a data set from scratch as efficiently as possible using ActiveLab and score all your data, get the ActiveLab score for each data point, which tells you how informative it will be to go get another label for that data point. Again, just in one line of code. And this works with all data modalities because all we want is that you have trained a machine learning model on your data set. You run the open source Cleanlab code that I showed before with the outputs of your machine learning model. And that makes this all work, across all kinds of modalities and across all kinds of machine learning models. And so this is a really flexible library that I encourage everybody to check out and see if it helps you improve your data. And beyond, so once you've discovered the issues flagged in your data set, for example, focusing on label errors again, one thing you can do is you can delete them or you can fix them, right? And so if you delete all the data that this package has automatically flagged and retrain the model, then you get some performance boost shown here. And if you go and fix all those issues, then you get a much bigger performance boost. In this case, we're doing an XGBoost model and we don't change anything about the model. We're just training it on improved versions of the same data set. And you can just see, how much better your model can get with no change in the model whatsoever. And so to actually fix these issues in the data set, this requires an interface fundamentally, because it requires you to bring in your domain knowledge. And so we've also built a no-code platform that runs all these same open source algorithms with automated machine learning methods behind the scenes to analyze your data. And then it provides an interface for you to really quickly fix up the data set. And yeah, it works for all kinds of data and really fills this gap in the AI enterprise solution landscape where it's hard to go from low quality data to a high quality model. And we think we've provided a pretty good tool here for you to try.